Imagine you have a magical box. You say, "I want an apple," and an apple appears. You change your mind, ask for a pencil, and a pencil shows up. You even request a unicorn, and there's a unicorn. The strange thing is this: the box doesn't decide what to create until you open it and look inside. Before you look, it could be generating anything. Only when you open the box does it choose and become just one thing: the apple, the pencil, or the unicorn. All of these possibilities exist simultaneously inside the box. This is similar to how particles operate in quantum mechanics. Before being observed, they exist in a state where they can be many things at once. When observed, they collapse into a single state. One explanation for this phenomenon is the Copenhagen interpretation. This interpretation suggests that observing a particle is what causes it to take on a definite state. This process is called wave function collapse. The act of measurement interacts with the particle in a way that makes it unable to remain in a superposition state. It must choose one single specific state. Let's step back a bit in the timeline. The ancient Greeks believed that the world was made up of 4 elements: earth, water, fire, and air, a revolutionary concept at the time. But after centuries, humans discovered that everything is made of atoms. However, atoms still weren't the end of the line. In the early 20th century, scientists like Max Planck, Einstein, and Niels Bohr began to unveil a stunning truth. Atoms were not simple structures, but instead contained even smaller particles: protons, neutrons, and electrons. And even inside protons and neutrons, there are quarks, particles that cannot be split further. These particles are believed to be the most fundamental building blocks of matter, and everything we see around us is made from different combinations of these particles. All the matter you see, from the chair you're sitting on to a star billions of light years away, is made up of these particles. But the story doesn't end there. Almost every particle has a corresponding antiparticle, which has the same mass but the opposite electric charge. For example, the electron has a negative charge, while its antiparticle, the positron, has a positive charge. When a particle and its antiparticle meet, they annihilate each other, releasing energy in the form of photons. Conversely, pure energy can also turn into matter, creating pairs of particles and antiparticles. Antimatter is extremely rare in the observable universe and is mostly created in particle collisions. If the Big Bang had created both matter and antimatter in equal amounts, they should have completely annihilated each other, and nothing would exist. And yet, we are here, which means there was a slight excess of matter over antimatter. Why is that? Physicists still don't have a definitive answer to this question, and it remains one of the greatest mysteries in modern physics. Quantum theory reveals that the fundamental building blocks of the universe go far beyond mere particles, extending deep into the very fabric of space and time. Within this framework, the universe is not simply made of particles moving through space, but rather a dynamic interaction of fields and forces woven into the structure of space-time itself. These fields, as described by quantum field theory, represent the true nature of what we call reality, with particles being excitations of these fundamental fields. Today, we believe that the deepest layer of reality consists of elementary particles governed by quantum mechanics. This invisible and incredibly tiny world is the origin of everything we see and experience. It is a world full of wonder and often feels extraordinarily strange. Visible matter is made up of atoms, which contain protons and neutrons at their center. However, protons and neutrons themselves are not the smallest particles. According to the standard model of particle physics, which explains reality at its most fundamental level, there are particles even smaller than these. Surprisingly, everything in the universe can be traced back to atoms. Atoms are the smallest units of matter that retain the characteristics and properties of the larger visible world, including both physical and chemical traits. Atoms are fundamentally quantum entities, with distinct energy levels, characteristics, and conservation laws. They interact with all 4 of nature's known fundamental forces. To understand more deeply, we need to explore the fundamental forces, invisible forces that govern everything in the universe. There are 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces plays an extremely important role in shaping the world we live in. Gravity is the force you feel when standing on the ground, keeping you anchored to the planet. Yet, it is the weakest of the four fundamental forces. In contrast, the electromagnetic force, or the interaction between charged particles, is incredibly powerful. It is this electromagnetic force that creates everything from light to energy, holds atoms and molecules together, and thus forms the objects around you. Then there's the strong nuclear force, a mysterious force that binds quarks together inside protons and neutrons. This is the force that provides stability to all matter. Although powerful enough to hold nuclear particles inside, it only operates at an extremely short range, much smaller than an atom. Finally, there is the weak nuclear force, which primarily influences nuclear decay and nuclear reactions in the universe. In a way, the entirety of physics can be seen within a single atom. This is what atoms can tell us about the universe. On Earth, there are about 90 naturally occurring elements formed through cosmic processes. Each element has atoms with a nucleus made up of protons, and possibly neutrons, surrounded by an equal number of electrons matching the number of protons. Each element has its own distinct properties, such as hardness, color, melting and boiling points, density, electrical conductivity, electronegativity, ionization energy, and many other characteristics. In daily life, we often take for granted the existence of certain rules, such as cause and effect. For example, something happens, and that causes a series of other events. Depending on what happens initially, different causes lead to different outcomes. However, in the case of quantum physics, the standard rules are completely different at the most fundamental level. You cannot arbitrarily determine your exact starting point, because there is always an inherent uncertainty in some properties of the system. There is no deterministic and precisely predictable way to describe how a quantum system will evolve over time. You can only calculate a set of probabilities. If you make a precise enough measurement, observation, or interaction, you will only see one result. However, that act of measurement, observation, or interaction changes the state of the system. This behavior has been debated for nearly a century, and the resolution is, you shouldn't try to interpret it. It may sound confusing, but it's precisely the interpretations that may be the obstacle preventing us from truly understanding quantum reality. Quantum theory, in its own right, is an extremely effective description of the microscopic world of atoms and their components. However, the disturbing part is that it also reveals a highly counterintuitive reality, where, for example, a particle can exist in a superposition state, meaning it can do two or more things at the same time. Returning to the magic box, that magic box is not just an interesting idea, it is actually the most comprehensible way to describe a core principle of quantum mechanics, the superposition state. In 1935, Erwin Schrödinger proposed his famous thought experiment to illustrate a consequence of quantum theory. He imagined a cat locked inside a box, along with a vial of poison. The decay of a radioactive atom could trigger a hammer to break the vial of poison, which would result in killing the cat. If the atom exists in a superposition state of both decayed and undecayed, then the cat would also be both dead and alive at the same time. The only way to know for sure is to open the box. This thought experiment brought the weirdness of quantum physics from the microscopic world into everyday life, forcing researchers to confront it. Physicists call these superposition states on a macroscopic scale, involving many atoms or other quantum entities, Schrödinger cat states. Over the past decade, these cats have helped researchers explore the transition between the quantum world and the classical world. They have also begun to explain why we don't see everyday objects existing in two states at once, and whether we might actually see such things in the future. The idea that a living creature could theoretically be both alive and dead at the same time is a classic example of the strangeness in quantum physics. Questions like, why and how does quantum physics work the way it does? Or do the mathematical objects in quantum theory actually represent something real? Have as many answers as there are people trying to answer them, but perhaps those answers say more about us, about our biases, assumptions, and preconceptions about the universe, than about the actual nature of the universe itself. There are very few things we can actually observe in nature. Properties of particles such as position, momentum, cross-section, scattering amplitude, and individual quantum states. Asking about the deep nature of reality assumes it follows rules that align with our intuition, but perhaps the opposite is true. Our perception of reality is limited by our senses and our own capabilities, and the true rules governing the universe may be far stranger than we imagine. We often talk about particles occupying specific points in space, but in reality, they are energy peaks or excitations in underlying quantum fields. For example, a photon is an excitation of the electromagnetic field. These fields permeate the entire universe, which means there is always a bit of photonness everywhere, the so-called virtual particles, which flash in and out of existence even when there isn't enough energy to create a real particle. Fields are considered more fundamental because the mathematical operations wouldn't work without them. However, the quantum nature of a field makes it impossible to observe directly. Any observation requires energy, which forces the field to create a particle. Therefore, we often talk about particles because that's what we can actually observe. The quantum world operates according to rules that defy common sense. A particle can behave like a wave under certain conditions, and even the concept of a particle becomes unclear the closer you examine it. Trying to determine a particle's exact position blurs information about its momentum, while measuring its momentum precisely makes its position uncertain. This is the Heisenberg uncertainty principle, showing that these properties are inherently fuzzy and cannot be known absolutely. The most astonishing thing in quantum physics is that, with just a few minimal properties, mass, electric charge, and angular momentum, a mathematical equation can fully describe that particle through a wave function that predicts its behavior in terms of probabilities. This concept is deeply connected with wave-particle duality and the principle of superposition. Particles exist in a range of wave-like states until observed, at which point their wave function collapses and they choose a specific state. The question then becomes, what exactly causes the wave function to collapse? The measuring device, or human consciousness itself? In the quantum world, contradictions and paradoxes are inevitable. Quantum paradoxes, where particles can exist in multiple locations at the same time. There are even paradoxes about time in quantum theory. Some hypotheses suggest that time does not always flow in a single direction. In fact, in some cases, time can branch in different directions, and it's possible that in extremely special cases, time could even stop or reverse. With these quantum paradoxes, physicists have proposed a bold hypothesis about parallel universes. According to this theory, every decision, every action in the universe could lead to a parallel world, where events unfold in different ways. So, could there be countless different universes existing at the same time, each with completely different conditions and outcomes? The multiverse theory has been introduced to explain the existence of these worlds. According to it, every possible outcome in this life corresponds to a different universe, where the storyline of your life could play out in an entirely different way. Even the smallest decisions in life could create parallel universes where each possibility is realized. This could help explain strange phenomena that we cannot explain in our own world, from supernatural events to mysterious occurrences that science has yet to fully understand. And then, there is another important factor that many scientists are still searching for an answer to: the role of consciousness. Could it be that we, the observers of the universe, can influence its very existence? Perhaps it is human consciousness that is the decisive factor in creating the universe around us. Quantum theory shows that space and time are not independent entities, but parts of a more complex system in which human consciousness plays an important role. It is our ability to observe and perceive the universe that may bring it into existence. So, is it the presence of human beings in the universe that truly makes it exist? Do things around us only exist when we are aware of them? And if we stop observing, could everything disappear into nothingness? So ultimately, what is it that makes science afraid? Some physicists suggest that by understanding quantum mechanics, we will understand the nature of reality. But what if reality itself is not real until it is observed? If each observation creates reality, then what determines what is real? Our consciousness, a measuring system, or is there something beyond both? This question not only confuses science, but also threatens our entire view of the universe. What's astonishing is that the very things scientists fear and cannot yet explain have already been realized in Buddhist teachings thousands of years ago, through mindfulness and inner observation. In the Heart Sutra, there is a passage that says, "Form is emptiness, emptiness is form." This means that what we perceive as shapes, forms, or matter is, in essence, empty, only appearances created by perception. Therefore, the question in quantum physics is consciousness necessary for reality to form, was already answered by Buddhism thousands of years ago. In the Buddha's teachings, there is a consistent and remarkably parallel view to the principle of quantum theory. All phenomena are created by the mind, meaning that everything in the world is a manifestation of consciousness. The external world has no fixed reality, but only exists in interaction with the human mind. Quantum physics states, there is no objectively independent reality outside of observation and interaction. We cannot say something is real without someone to measure or observe it. Correspondingly, in the Buddhist teaching of dependent origination, or pratityasamutpada, the Buddha said, this exists, so that exists. This ceases to be, so that ceases to be. Nothing exists independently. Everything arises from mutual relationships. This is one of the most distinct intersections between Buddhism and quantum mechanics. Quantum mechanics rejects fixed reality. Instead, it describes a world of probability, constantly in flux. In relation to Buddhism, Buddhism emphasizes impermanence. All things arise and pass away endlessly, with no fixed essence. An electron is not somewhere until you measure it. It only has probabilities of appearing in different places, just like human life, always changing, elusive. Life and death could be separated by just a single instant. Buddhism, with thousands of years of introspective contemplation, has long proclaimed, the outer world is just a reflection of the mind. To understand the world, understand yourself. The convergence between quantum physics and Buddhist philosophy is not a coincidence. It is a sign that modern science is approaching the spiritual intuition of ancient humanity. All right, let's stop here for today. Feel free to leave a comment on this topic. See you in the next videos. Please like, share, and subscribe to support the channel's growth. Thank you, everyone.